Good morning, guys, and welcome to the third week, basically, of this class. This is kind of a little bit loaded in a sense that there's a lot of materials that seem to be basically coming along, especially if you did not have optics in the past. So it may sound that there is a lot of materials to cover, but it really is based on two laws, okay? And I'm going to explain of them. One of them is straightforward, okay? So it's the second one that is a little bit, quantitatively a little bit is more involved, and it involves trig functions. But even that, probably we're not going to get into a lot of calculations based on that. So it's basically just the idea behind it. So what these topics are about, so let me share with you first of all the screen. And okay, let me first of all prepare the screen because I don't want to, I'm still not finished with the homework, basically trying to see what problems are useful and to reinforce basically the concepts. We go back home, and yeah, so let me share the screen. So basically, as you can clearly see, this is the content for this week. This homework is still not published because I had to make some changes to the problems. I know I posted it earlier, but then I had to reconsider because of the fact that there are some problems that need to be included and some that are actually repetitive and there is no need for them. So that's why I'm actually making those changes. So I hope to have this done by this afternoon. When we meet next time around on Wednesday, we're going to finish the concepts covered in this basically chapters. And then we will discuss some of these problems. Basically, the promise is we'll go through some of them. Some of them are actually, you will see, involve a little bit of geometry. So you will need the ruler, a compass, and maybe protractor. I don't know. We will see. And you need, of course, a pencil to do them, because all you have to do is just draw. You're given an object, you're given a mirror, whether it's a flat mirror or concave or convex, and you're supposed to find the image. And you're supposed to find it with a ruler and protractor, basically trying to use the ruler to find it. Okay, so we'll try to do something actually part of the homework assignment there too. And also some others, they rely on what I already alluded to, namely the two laws. They're called Snell's laws. And we're going to use those to do some basic calculations for the magnifications and things like that. So let's look at the learning objectives for this week, because we have quite a few. First of all, they're here. And then we have this videos that hopefully reinforce what we're talking about. And they're about altogether, I think about 30 minutes or 35 minutes combined. So, and they're divided into chunks so that you watch the first 10 and then go into something else, the second 10 and so on and so forth. And then the last two are kind of lighter. So those are the idea behind it. Then we're going to get into, at some point this afternoon at 12:45, we have a lab. And lab deals with these concepts that are covered in here, and actually goes a step beyond because it gets into spectroscopy, okay? And that's basically in a nutshell what we have for this week. So let's get into the objectives for this week. So they are listed in here. So we're going to talk about the nature of light. We'll try to understand what light is, and we're going to take it in a historical context. Then we're going to look into the law of reflection and how we apply it, the law of refraction and how we apply it. So those are the two laws I've been talking about. The law of reflection, light hits a screen or an object and bounces off of it. That's basically what it is. There are two kinds of reflections. There is the specular reflection and there is a diffusion reflection. So specular reflection is what you do when you stand in front of the mirror and you see yourself on the other side of the mirror. So that is what we usually talk about when we refer to a reflection. There is another kind of reflection is when you look around you anywhere, there is probably a wall, there may be something in front of you like a cup or something like that, your phone or whatever you have in front of you. Those, they reflect light as it bounces off of them. If they are colored, they reflect more that color and absorb the other colors, but they reflect it in all directions, okay? And like the ones that has a mirror that reflects it only in a specific direction because it's smooth. Okay, so that's the big difference, other than the fact that the other surfaces are kind of not as smooth as the mirror is. So that is basically the big difference. Okay, and then we're going to talk about lenses. Lenses is what is actually in your glasses. Okay, if you have some, if you are wearing some. It's also when something that is typically actually in your camera, even that of the phone that has lenses, and then also all kinds of optical devices. Okay, they use lenses. Sometimes lensing happens naturally, and sometimes you have to be manufactured. At least that's the purpose of it. There are two kinds of lenses. There is a convex lenses, and there is the concave lenses. So this is a lens that is, I mean, a mirror that is concave, I should say, or a mirror that is convex. So basically, which side is the reflective side? Is it on this side? This is basically the side that is coated, and this is the side that is reflective. In this case, we have a concave mirror, and the opposite, if it's true. I mean, if you look at the side of your car, it has a convex mirror. Okay, so in that case, it's this side that is reflective, that is smooth, and the metallic part that covers the inside, the coating, is actually inside. So those are the types of mirror, and it applies also for lenses. Lenses also have bulging, and that is actually convex lens. And sometimes they have actually opened this way, so they're concave. Sometimes actually it's a combination. You could have a flat side and actually bulging. So this is actually a combined lens, or actually it could be both. Okay, especially for lenses, convex on one side and concave on the other side. And so those are the two types. Or it could be basically, depending on how you're going to construct them, convex from both sides. So those are the types of optical devices that you have. Obviously, they have a purpose, they have properties. All optical devices have focal points, including the flat mirror, except the flat mirror has a focal point that is far away to basically located. But that is basically some of the idea behind this whole thing. Sounds good, everybody? That's the plan. It's all about optics, light. You guys agree with the plan? Let me prepare my notes.
Yeah.
Okay, thank you, Ralph. Okay, let me get into the, okay, thank you, Nayali. Let me get into the OneNote. It's in here. So let me make sure it's prepared. Okay, it is. So let me share with you. So light was a puzzle for a long time, and historically, it was one of the issues that people tried to understand. Okay, until the work of basically, I mean, it was a phenomenon. Basically, a reflection was known. So this is one part that we're going to talk about. So let me change the color of the pen. Let me make thick enough. So basically, the first thing that we're going to be talking about is the law of reflection. So we're going to start with that. I mean, if you have a shiny surface, or if you're looking at the surface of water, for example, you see the reflection of all of the materials above it, trees and whatever you have, your birds flying and whatever you have in there. So this is the first thing, is a reflection. There is another phenomenon which we're going to talk about, and I'm going to demo it for you, which is called the refraction. That too is a known phenomenon. Okay. Here, it's easy to think about it. This is in a nutshell what the law says. This is a reflective surface. Reflective surface. In other words, beneath it, there is some sort of coating, prevent light from going anywhere, and usually that's a metal, okay? Silver or whatever you have, okay? And you have a shiny surface, usually made out of glass, okay? So this is a flat surface. So what you have in this case, you have a ray that comes on one side. So that falls on the surface. So this is a ray. We call it an incident. Okay, so it's coming to the surface. So what happened, the law says is, oops, the outgoing ray The outgoing one basically is going to be in a direction. So this is the reflected. Is going to be in such a way that these angles are the same. So if I take the normal to the surface, if I take the perpendicular to the surface, this is the reflective surface. If I take the perpendicular to it, the incident angle, which conveniently usually we give it this the Greek letter theta, and I for being incident is the same as the outgoing angle in this case for the reflected angle, which we're going usually we give it the symbol theta and also the angle r. So this is the first law. The second law, and that is really why I brought them immediately together, has to do with the law of refraction. So this is a known phenomenon, the reflection. The refraction is a little bit more tricky, and this is according to Feynman, the only experiments the Greek did. So what you have in this case, you have two surfaces. Usually one is denser than the other, denser and lighter. Okay. In this sequence, think of it that this is water. And this is air. So beneath this surface, I have water in here. And if I draw again that normal, so this is the same normal that makes a 90-degree angle. And it can, in fact, let me change the color in here a little bit to see if I can get into a different, yeah, let's use green in here. So again, this is my incoming wave. Oh, do I have a thick enough? I think it's thick enough. Okay. So, what is it? So this is the ray that is going to be incoming. So this is again the same thing. This is an incident. So this is the ray that is coming on the surface. But this surface now is not coded in a sense that the ray can go through. Well, it is not going to go straight on a line. And because I chose it this thick, then it's going to bend toward that vertical. So this is the bending of light due to the separation of two media. One medium is denser than the other. So in this case, again, according to my symbols, this will be the angle of incidence. It has the same symbol, theta I. This is the angle of refraction, theta of refraction, okay? As opposed to this one being reflection. Well, there is a complicated mathematical equation. It has to do with the index of refraction, which we're going to explore. So it has to do with the angle of index of refraction of the immediate medium, which is for air is 1, and for water is actually equal to 1.33. So that has to do with something else. And we're going to explore all of these ideas. And the law basically says that there is a mathematical expression that is says like n of the first medium, let's put it 1, times sine of theta 1. So I change the symbols to this one to 1, and this one to 1, and this is to medium 2, and this is medium 2. So just to keep up, so they have two media, medium 1 and medium 2. So this is medium 1, medium 2, to stay in general instead of talking about air and water or something like that. This product of the index of refraction, so what is this one? It's an index of refraction. Every material has it. And we're going to explain what that is. It has to do with the speed of light, actually. This two are equal. N2 sine of theta 2. So this is actually a little bit complicated, and this is one of the first, or at least according to Feynman, the only documented experiment. So this is, I gave you the end game. I gave you where we're supposed to get in terms of loss. Okay, so let's talk about historically and how what happened in here, at least later on, we're going to understand this thing. So this is based on experiments. So this is based on observation. That's the one that led us to this law. So these are called Snell's laws. These are called Snell's laws. Oh man, I wanted to get into that region and I cannot do it for some reason unless I get some sort of a... Anyway, so historically light was a mystery and people wanted to understand it. So there were a lot of thoughts about this one. The first document thoughts were actually done by Mr. Alhazen, who lived in modern day Egypt and also Iraq and all of that. And he was only about a few centuries or 1 century just before Mr. Newton and Galileo and all of the other people. And he developed experiments, and he was actually the person who laid the foundation for the scientific method. And he's the one who actually promoted the idea of hypothesis and testing the hypothesis and all of that. So basically, he started testing with light. One of the things he wanted to do is the speed of light. And he argued that light must have a finite speed, basically, because it's coming from all of these dots in the sky, which are stars. And if it did not have a finite speed, and if it reaches us immediately, the sky should be completely lit out with them, and we cannot really see, the day and night would be the same, okay? And then also he conducted experiments, basically because at that time in the desert, you live in the tent, so all he has to do is make a small hole and then sees the laws basically of refraction and refraction. So his hypothesis was light actually was made out of tiny particles, and those are the particles of light, okay? Mr. Newton took it a step further, and he explored the same ideas, and he published the book that is known under his name for the optics, okay? So the idea then now is known actually Newton's corpuscular nature of light. So that's basically how it is known nowadays. Basically, that light is made up of tiny particles. That's what corpuscular means. That's made of particles, okay? Tiny bodies. And they are moving straight out. The reason why this is actually makes sense is because if I take a tennis ball, for example, and if I go to the wall and throw the tennis ball in one direction, it's always going to bounce in the opposite direction in such a way that the angle of incidence is equal to the angle of reflection. Why? Because of something that we're going to later explore called the conservation of momentum. The momentum in this direction, in the vertical direction, it must be maintained, and the momentum in this direction also must be maintained. And in this case, it's only just, if I take a ball, that's what the second point is, and straight out, it's going to bounce immediately back up. Because there is no momentum in this direction, it's only in this direction, so there is conservation for it. But if I give it an angle in here and throw it, it's always going to bounce in such a way that the angle of incidence and the angle of reflection are the same. So that is the idea behind it. So Mr. Newton gave it some weight because of the fact that he actually put the mechanics in place, and we have an understanding of this one in here. So that's basically, light is made up of tiny particles. You really need to hold to this idea that light is particles, which is a big deal. Yes.
Could you make the notes big again?
Okay, let's see. Okay. Sounds better?
The notes are still really small.
Can you make it any bigger?
Yeah, like they're not, we see you, we don't see the notes.
You're not looking at the shared screen?
Now it is.
Oh, I thought I had shared the screen for some reason. Okay, so let me go back into the reduce the view. How is it now?
That's good.
Okay, so basically, as I was saying in here, let me put this screen in here a little bit. Are you still looking at the stuff that I'm looking at?
Yes.
Okay, thank you, TJ. Anyway, the point being in here is that light is made up of particles. That's really the point that you need to understand. The reason why this is so is because we're going to go full circle. Mr. Young later on in the early 1800s, 1805 or 07, I don't know exactly the exact date. He made experiments, and he argued beyond the shadow of the doubt that light is not particles. But actually waves. And that is the lab today. Okay. Mr. Maxwell later on made actually a better explanation of why so, and that is because light is made up of spectra. So basically light doesn't matter. So if you have the red in here and the blue in here, you have somewhere in here the green, you have somewhere in here the yellow, and you have somewhere here the brown, anywhere in between them. Okay, these are spectra of the electric field and the magnetic field, and that's what Mr. Maxwell has argued. Again, this is part of the lab today. Okay, so we went from the idea that Mr. Newton has proposed that light is particles, and he made a good justification based on the momentum of particles and how they interact with the walls, and how that is similar to the law of reflection, and how is that similar to the law of refraction. Okay, to no, that's not true. Light is not particles at all, it's waves. Okay, and we're going to explore that idea today in the lab. To back toward the end of the century, we're going to explore this idea later on, that light actually is a wave, according to modern quantum mechanics, that actually Mr. Einstein is the one who made that argument. Light is a particle called photons. The first photon, the word photon was actually first introduced by Mr. Einstein, and now it's used for light all the time. So light is a particle. So which begs the question is, what is light? So light, in a nutshell, is a particle and a wave. Those, they may sound kind of a little bit just words, but they're completely different. The second one means it's not a particle. The first one, it means that it's not a wave. So this duality, this what appears to be a contradiction, is what light is. Okay, so that is in a nutshell what light is that we know today. It may sound contradictory, but that's exactly what the answer to this one is. That's basically in a nutshell what light is right now that we know of. Sometimes it behaves like particles, like in this case, behaves like particles. In this case, behaves like particles. And if you have a photovoltaic cell on your a solar panel on your roof or somewhere, it's behaving like a particle still. All of this can only be explained if light is particle. If we're going to do the experiment today, you will see light is actually not a particle, but rather a wave, which is not a particle. It's not just, it's a different, it has a different, it's not like a description. It's a completely different thing. It's a wave. So it behaves like waves, the one that we explored from the previous chapters. So that is basically what the nature of light is. So that's where we are is. So the question that Mr. Alhazen and other people before him were struggling with, what is the speed of light, was resolved later on due to two major experiments. Actually, the problem is still going experimentally, but we know today the speed of light, exactly how much it is. Okay. Initially, the first experiment that was done by Romer, basically what he did was he theorized that, okay, here is the sun. Here is where the Earth is. And at some point, Jupiter would be here, for example. It's about 5 times further from the Earth. Jupiter has a tiny moon called Io. Not tiny, it's bigger than the Earth's moon, okay? So it's big moon, but relatively speaking, compared to the planets, it's tiny. So you have a moon called Io. And if I look at Io from the Earth today, for example, Io takes about almost 2 days to go around Jupiter. Okay, light that shows this phenomenon, how long it takes for Jupiter to go around how long Io will take to go around Jupiter, is this distance, whatever that distance is. So we don't know. Let's call it. Okay. So it comes in from here and it hits us. This distance is tiny. If it doesn't, it's negligible. We don't care about that. And this is the Earth-Sun distance. We know that this is by astronomical units, called an astronomical unit. This distance actually is 5 minus 1, which is about 4.2 astronomical units. So this is actually a known number, okay? Even during that time, even during Mr. Romer's time, okay? Then if I wait 6 months from today, this is what happened. The sun stays in its place. The Earth 6 months from today is going to be here. So this is where the Earth is because it's going around the sun once every year. So it was now here, 6 months later is going to be here. Jupiter would have barely budged from its place because it's very far away from the sun. So it's not going to be far from its place. So I have to wait a few days only for the Earth to position itself in the opposite direction. So how long light now will take? It takes this distance, 5 astronomical units or 5.2 plus this 1 astronomical unit. So altogether, light now coming from the same phenomenon of Io going once around Jupiter, it's going to take 6.2 astronomical units instead of 4.2 astronomical units, because the Earth goes around the sun, which is 1 astronomical unit all the time. Astronomical unit, so that you guys know, is 150 million kilometers. It's a big number, or 93 million miles. So that is basically the distance from the Earth to the sun, but we're looking at about 6 times as much for the second case, and only 4 times as much for the first case. Based on this measurements, this is Mr. Romer, based on this measurements, he found the speed of light to be about 200,000 kilometers per second, based on the period, the time it takes for Io to go once around the sun, around Jupiter, I'm sorry. So based on that and the shift in frequency, the shift in period for that moon, he found that the distance is about 200,000 kilometers. Obviously, he did not have really precise measurements for the period and also this distance, so otherwise we would have come up with a better measurement. And even then, this calculation carries with it a big error anyway. So another experiment that was done by Mr. Fizeau, basically, so what he did, he has a source of light and he has a gear, basically, system that is revolving, and I think it has a description for it in the book in here in detail. So the grooves in here in the gear are separated by a certain distance, and as the gear rotates, he has a specific measurement for this distance between the grooves of the gear. So he can control that. He can. This is Mr. Fizeau's experiment. He's a French physicist. Okay. So what he did was, he had the apparatus sitting like this. So you have a source of light in here. And you have the gear system mounted in here. And then he has a reflective surface in here. So as the light goes through the grooves, it's going to bounce back. Here is the adjustment he had to do. If when the light comes back, it's going to hit one of these grooves, of course, he's not going to see it. So here's the source, and then nothing comes back. But if he adjusts in such a way that as the light comes back, it's going to come back to the next opening, basically in the groove, not in the tooth, but in the groove itself, in the opening. Then in this case, he can find the right frequency where light basically would have traveled back and forth, and this one would have spun just enough. And he knows this distance, of course, that's part of his experiment. He can find the speed of light. That is when he came up with a better number for the speed of light, which is about 300,000 kilometers per second. He had some errors in it initially, and the experiment was refined further, and it was refined further and further. Today, the number is actually 299,794 or something like that kilometers per second. But usually in calculations, we take it to be 300,000 kilometers per second, which brings me back to the observation of Mr. Alhazen, and actually before that, I mean, after Mr. Alhazen, but before this experiments of Romer, there was actually another experiment that was done by Mr. Galileo. And Mr. Galileo, basically what he did was he stood in one side of the mountain in a barn, okay? And then he had a friend about a mile away, to basically also standing in a barn, and both of them have a, not a candle, a lighting system, okay? I forgot the word for it. So now here is the thing. He tells him, okay, I'm going to light mine. That's Mr. Galileo. And he told his friend, who is sitting about a mile away from him on the other side, he told him, when you see the light from this source, light yours, okay? So Mr. Galileo, what he did was, he didn't have a watch, he didn't have a clock, he didn't have anything like that, fancy things. So all he had was a pulse on his arm. So what he did was, he lighted the light from his side and waits for when his friend basically light the other one. Meanwhile, he's counting the time using the pulses on his wrist. So he lights his, started counting the pulses, and wait for the time for the light to bounce back from his friend. So he assumed that, okay, if I light mine, the light will take the time to go from here. And then if my friend, so this is the first light so that my friend receives. And then it takes another time to come back from his friend's light, okay? And based on that, he knows the distance, which is about 1 mile. All he has to do is find the speed of light, because light travels 1 mile and comes back another mile, so it's 2 miles divided by the sum of the 2 times, okay? Which is really what he's measuring, because that's what he's measuring. He lights his, and then he waits for the light to come back. So this is actually what he measures. This sum is what he was measuring. So this is how he figured the speed of light is. Mr. Galileo, in his documentation, put a lot of numbers together, but at the end, it did not make sense to him, because he brought him in, because he suspected something was wrong with his experiment. He brought his friend in to closer to him in the same barn, and he said, okay, we're going to do this experiment in here, not 2 miles, just in here, okay, the 2 of us. I light this one. He started counting, so don't do anything until you see the light, okay? And they're sitting next to one another, okay? So don't turn on your light until you see the light that is from this one. So he turned his, and then start counting, and then his friends turned his, and then Mr. Galileo measured the time. He found that there is no difference between the experiment 1 mile apart and when they are in the same place. Light travels, doesn't matter for this distance. And the reason why it doesn't matter, first of all, he immediately threw all of his data and said they don't make sense, because basically I suspect what I'm measuring in this case is the reaction time, because that's all he was measuring, is how long it takes for his friend to react and how long for him to react to his friend's reaction. So that's basically how Mr. Galileo argued that. And at the end, basically, the whole experiment failed because of this thing. And the reason why it fails is because 300,000 kilometers per second, which is roughly about 200,000 miles per second. 1 mile is nothing. So light takes blink of an eye to travel that distance. I mean, not even a blink of an eye. So it takes a lot less time to do that. So that's why his experiment was failing. Had they stayed probably maybe the distance from the Earth to the Moon, one of them is on the Earth, the other one on the Moon, it would have taken about a minute. A second, I'm sorry, second. Because the distance from the Earth to the Moon is about 384,000 kilometers. So if you stand on the Moon, it takes slightly more than a second for light to reach you. So it's almost real time, but there is that measurable time probably that you could find, but not if you are a mile away, not if you are 10 miles away, not if you are in 2 basically different kinds of, not if you are in the East Coast as to West Coast, 3,000 what miles, 5,000 kilometers, still nothing basically for light to travel through. That's really what made that experiment fail, is the fact that the distance that he was using is nothing. And at the end, he recognized it because of the fact that he was measuring reaction time. So this is the experiment of Galileo. And that way basically failed, did not work. But Mr. Romer's experiment was a little bit better. In a sense, it brought us a very good answer, but not good enough, okay? What it did, though, it proved beyond the shadow of the doubt that actually light has a finite speed. So the argument that was posed before, that light could not have an infinite speed, is critical, because otherwise the night and the day will be the same, lit by as much light, because the further away the stars, they would send their light immediately to us, or the closer ones like the sun, and we would be flooded with that light. But we don't see that, then light must have a finite speed, and here it is. Here is an order of magnitude for it. And as a matter of fact, when Fizeau refined the experiment and later on further observations gave us even a better estimate for that light. So light has a finite speed. This speed is in vacuum though. So this is in vacuum. Okay. But and it's also the speed in air. So in air, it's about 300,000 kilometers per second. Usually we write it at 3 × 10⁵ kilometers per second in scientific notation. But since a kilometer is 1,000 meters, we write it at 300 million meters per second. Okay, it's the same thing. So if you see a number like this one, this is still the speed of light in air or in vacuum, void, okay? In water though, light travels slower. In water, the speed of light is actually equal to 300,000 kilometers per second divided by 1.33. In glass, it's about 1.5, basically. So this is in water, this is in glass. Okay. In general, in any material, the speed of light is 300,000 kilometers per second divided by n, where n is index of refraction. Now, here is this material that I'm talking about is a material that is transparent. Okay, index of refraction. So that is the one that I was referring to in Snell's law. So this is this n in Snell's law. This one. So a medium 1 will have an index of refraction n1, and medium 2 will have an index of refraction 2, n2. So that is basically what the essence of this index of refraction is coming. As long as the material is transparent, this is what's going on in it. But there are different kinds of materials. For example, the window has an index of refraction, and light can go through it still, although slower, but and you can see outside what's going on. You can see the cars, you can see the trees, you can see whatever is on the other side of the mirror or the window. However, on the wall, you don't see anything on the other side. So there is, in addition to transparent materials, on the opposite of that, there is the opaque materials. So those are the two main different materials when it comes to light. So either they don't let light go through, like in the case of an opaque, like wall, or they let light go through, which is in the case of a mirror, or I'm sorry, window. Glass, that's the point, okay? Glass, to be more specific. So those are the two different kinds of, so what's going on inside a material? Let me explain a little bit in general. So this is what's going on, whether it's transparent or an opaque. So I think this is material made up of course, different molecules and different atoms in it. And each one of them, each atom in here, so this is nucleus, and these are the electrons. I'm just taking two shells in here of electrons. So here is what's going on. Light comes in, which is a wave, is going to basically, if an electron was sitting in here, the electron will absorb this energy and get excited. So it's going to move up, okay? But then what happened, this is an excited atom. It's going to go back to its ground state by re-emitting that light. So it's initially it's excited, then it's going to emit that same frequency by having the electron bounce back to where it came from. So what's going on in this case, then that same light is going to be re-emitted again. So the next atom now will do the same thing, will absorb that electron, I mean, the electron from that atom will absorb that light and then get excited. So the atom now is excited all of a sudden. The next door neighbor is excited now. And then it's going to stay excited for a little bit, and then it's going to re-emit that light. So what happened in here, light actually between an atom and an atom is traveling with the speed of light. It's traveling with 300,000 kilometers per second. But for a short moment, light is not traveling because it has been absorbed by an atom. And then, for example, in the case of water, and then the atom is going to get excited. And after that is going to re-emit it. During that moment, light is not going anywhere. So during that moment when light is slowing down, actually, it's not slowing down. That moment, light is not being transmitted at all, period. And then it's going to be transmitted by the speed of light and so on and so forth, until light will emerge at the end of the day with the same frequency that came from the other side. So that is basically the same color, okay? So if we have white light, it's going to be more or less on the other side with white light. Materials though, like for example, windows, they have this weird property, okay? They don't transmit infrared. Okay, long wavelengths, they don't go through them. Actually, if you shine an infrared light on a glass, for example, they look opaque. You don't see anything. But because light that we see has all kinds of wavelengths, including the infrared, we see the light, the visible light going through them, but not the infrared because we don't see it to begin with. I mean, case in point, if you have a car sitting outside in the sun, radiation from the sun will go through the windows inside the car. Then that radiation is absorbed by the material of the car, basically the seats and plastic, whatever you have in there. Their temperature will increase because their energy has been increased. So what they do, they re-emit that light. They re-emit it actually in infrared. Now, infrared does not go through the window, so it bounces back and it stays in the car, and the car basically will heat up inside. That's why it's not advised to leave children in there and lock the windows on them, or pets or anything like that, because their temperature will increase so high, because the temperature has to do with the infrared light. So what's going on in an opaque material? That's exactly what I was describing in an opaque. So this is transparent. In an opaque material, it's the other way around. Basically, what's going on in this case is the molecules usually are the ones that are involved, not the single atoms. So the molecule, this molecule, for example, absorbs that frequency, which is usually in this case infrared. So it's a low frequency, long wavelength. So it absorbs it, and when it absorbs it, instead of re-emitting, it's going to be just moving around back and forth more. Okay. So it's going to get excited and start moving back and forth. The temperature increases. And even in case of the wall, for example, it's going to absorb that radiation, but it takes it internally, somehow distributed between energy of motion and other kinds of energies, and the material will retain that light and never transmit it on the other side. There is actually penetration depth, usually for light. It comes in from one side, and depending on the thickness of the material, the light will only be penetrating up to a certain point, and it's absorbed in here. It will never reach the other one. So those are some of the properties of material when it comes to light. Some of them are transparent, some of them are opaque, and the opaque do not transmit anything on the other side, basically. And even the transparent, for some frequencies, they are opaque for others. So that is some of the properties, and this is the essence of the greenhouse effect, actually. Greenhouse effect is due to this peculiar behavior, that some frequencies are more transparent for others than the other way around. So that is basically what the argument in here for the greenhouse effect. So basically for greenhouses, when you're trying to grow tomatoes or whatever you're trying to grow, you have the light coming through the plastic, which has similar properties like the glass, or the glass for some greenhouses. So it goes in, it's absorbed by the plants and the soil and the ground. So that frequency is the light, the visible light, but then those get excited and they re-emit it back. So the material in here will re-emit part of the energy, but usually in lower frequencies, longer wavelength. So now it's in infrared, but it is not going anywhere now. It's not going to go through the greenhouse again, because that is reflected back inside, and the temperature keeps on increasing. The greenhouse effect also is the same one that is causing global warming, because the atmosphere also behaves in a similar fashion. Radiation from the sun comes in all kinds of wavelengths. The Earth absorbs it, and then when it transmits it back, it's going to be reflected. Just like the few days that happened in the past week or so, when we had high humidity in the atmosphere, that the water basically is a good also greenhouse material. So it's going to absorb it and bounce it back, and the humidity basically causes the temperature to increase, and then although we are at night and there is no source of heat anymore, but it stays hot. So these are the phenomenon that we're discussing in here. One of them is transparent materials and others are opaque materials. So that is basically the index of refraction, and that is in a sense the law with which that we're going to be exploring these things in here. Again, as I was saying, for a transparent material like glass, if I take a glass in here and put a coating on the other side of a reflective material, usually it's a metal, this is a flat mirror. One of the homework problems takes an object. So this is the mirror. This is an object. And you want to find its image. So what you do in this case, if you have a ray that is going, if you look straight up, okay, you have a ray that goes from here, it's going to bounce back in there. Why? Because the angle of incidence is 0 and the angle of reflection must be 0 because of this condition, this law. The angle of incidence and the angle of reflection. When it comes straight up, right on the vertical, it's going to bounce back right on the vertical because the angle of incidence is 0, collapses on itself. So the angle of reflection is also 0. So for an outside observer, the object in here appears to be coming, or the image appears to be on this line, anywhere on this line. Okay, could be here, could be here, could be here, could be here, actually in front. Okay. If I look at it from a different perspective, if I'm sitting at a different position, here, for example, so this is my sight in here. The ray that is coming from the object, here it is going to be bouncing back to my eye on this direction. So this is the reflected ray, and this is the incident ray. The angle of incidence must be equal to the angle of reflection. So these two must be the same. These angles must be the same, and this is what I see in there. This is the normal to the surface. So for me, looking at this from this position, the image actually must lie somewhere on this direction. The combination of these two is where the actual image is. So this is where the image is. This is by construction. So this is how the image was formed. Now, if I go behind the mirror on the other side of the mirror, do you think I will see the object or anything in there? And this is a question for you guys. You need to tell me. I mean, you're standing in front of the mirror and you go and peek behind the mirror. Would you see something standing on there that looks like you? Yes or no? You guys understand the question?
If it's a mirror, I don't think so, no.
No, actually, if you try it today. Go in front of the mirror, put your hand on the one side and look, is there another hand on? It's not. So this is not a real image. Why would I say it's not a real image? It's not because there is nobody in there. Because if I take a film and expose it on the other side, the film will not develop. I will not get an image. Make sense? If I have a mirror here and quoted on this side, this is the reflective side, and I take this pen and in front of it, I will see an image in here. So I say, okay, wait a minute. The image appears to be coming from the other side. So what I do in here, I bring a film and expose the film for a short while. and then go and develop it, I will not find an image. Nothing will form. The image, the film will be completely exposed and nothing will come out of it. Make sense? So this image is not a real image. Not a real image. Why? Because if I put a film in here, I know probably some of you are not familiar with films. In the old days, we have 35mm films, and those are the ones that you take pictures with. Now it's all of it CCDs, but that's a different technology. But if you, what a film is, basically, it's a material that is kind of sensitive to light, and if you expose it to light, it's going to completely be coming white. But what happened was, if you have an object in front of it, if you're standing in front of the camera when it's in that, basically what it does in this case, it leaves an imprint on the film that is a reflection of what is there. Okay, and that reflection, it comes, of course, dark, black, depending on what's going on in there. You take it into the development room, and you make those becomes a negative, so you make now an image out of it. Okay, so that is how films used to be developed in the old days. Okay, but if you do that in here, you're not going to find an image. So this image is a virtual image. So virtual as opposed to real, not real. Okay, this you cannot. I mean, if you take a lens and you put an object in front of a lens or a mirror that is transparent, I mean, that goes through and through, and you expose a film on the other side and you have a source of light, you're going to find an image. That is a real image. This one is not. So this is a virtual image, okay? So why? Because again, we're assuming that there is some sort of a source of light somewhere in here. There is a light source in here. And that light source is hitting the material and reflecting back on it, okay? Because this material, and the explanation is in the videos in there, has properties where its surface is not as smooth as that, for example, of a shiny surface. So this is what a surface is of a regular material. It's rough, basically, surface. I try to exaggerate in here. So the light that is coming in here will be reflected. So this is the normal, will be reflected in this direction. The light that hits it in here, actually in this point, so this is the normal. So the same light that comes in here and hits it on the normal is going to be bouncing back in his direction. So you have light bouncing in this direction, you have light bouncing in this direction. So if I take, for example, this surface that somehow gets a light, let's say, for example, this one. So the light is coming still from the same source in the same parallel direction, but now it's going this way. So you have light going this way. So I'm going to count them. This is 1, this is 2, this is 3. So you have light that is bouncing this way, light that is bouncing this way, and light that is bouncing this way. So it's diffuse. So because all of this is just a surface, a tiny, tiny, tiny area of the surface. So it looks like it's actually, for me, looking at it, this is what the source is. So light is going in every which way, okay? And that's exactly what's going on. So part of the light that's going every which way is going to go hit the mirror and come back, and the other part is going to come in here and hit my eye. And that's how I make the image of this object. It looks like it's in here, coming from this direction. Okay? Because I combine all of these sources. Yes, I have all of these sources, leaving this one going in every which way, but they are all pointing to the same source. So this is the object, and this is where the image is, because it's also similar to the object, except lights seem to be coming from another point in the space, and that point is behind the mirror, and that is how the image is formed. So this is how the image are formed on a flat surface, okay? Now, as opposed to a flat surface, we have other kinds of mirrors that we can consider, and these mirrors are the following two shapes, okay? I have a concave mirror, basically, that has a curvature. So it's a curved mirror. And I come in here and coat this side. Put my reflective material on this side. So if I do that, this mirror is a concave mirror. So what's going on in this one in here? Every point on it, I can draw the normal. On the axis of symmetry, it's a preferable point because this is the perpendicular to it. So it has a curvature of some sort, and this is the axis of symmetry. And the curvature is a circle. So think of it as not really a circle, more of a sphere. Okay, so you have a spherical object, and you cut part of it. So it looks just like this opening, not a circle, not a part of a circle, but rather part of a sphere, because the entire shape looks like it's a big dish that has an opening. As a matter of fact, they're called dishes. This is the one that is used for the antenna for the reception of TV. Okay. So for this one, there is an axis of symmetry, and there is a curvature center. So this is the radius r of the curvature. So think of it, if it was a sphere, this is where the center of the sphere is, and this distance is the radius of the sphere. So this is the radius r of that surface that curved mirror that I cut it from a big sphere. Okay. If I do the math, the focal point is going to be half of that distance. Okay, so this is the focal point. So what in the world is a focal point? Let me explain. If I have a ray coming from infinity, far away, that ray is going to obey Snell's law, which is the law of reflection. So the light will reflect back on this surface, on this point. Okay. And it doesn't matter which ray I take coming from infinity, they all will bounce back on the same point. So if I take another one coming from here, for example, but also it's going to reflect on another surface, and the angle will be a little bit smaller, but at the end of the day, it passes from the same focal points. And if you have it coming from this side also, so if this is the incident ray, all of this are the incident rays, okay? Then the reflected wave is going to pass through this point again. So they all pass from the focal point. So rays coming from infinity, they will bounce on the same point. This is part of the parabolic and parabolic basically shapes. This is what the parabola is actually, okay? For the case of a spherical mirror, they're not exactly parabolic, in a sense that, especially with different frequencies, there is a shift back and forth, but it's very good close approximation if the curvature is big enough, if R is big enough, compared to the cut, to where you make the cut, okay? So if you're in the business of making antennas, if you're in the business of making mirrors, which is really very, very delicate job, then you would want it to be as parabolic as possible so that all the rays will bounce back on the same point. This is what by definition is the focal point is. Oops. So this is where the focal point is. So focal point is where all the rays coming from far away reflect to. Okay, so they come in from far away, they hit the mirror, and then they reflect, and when they pass through the focal points. Okay, so finding where the image is kind of tricky, depending on where the object is. So if the object is in here, the image that form is somewhere in here. So if I take really a film, okay, and I put it there, it's going to develop. So the question now, this image is real. It's inverted, and its magnification is less than 1, but it's still real. If I put a film in there, it's going to develop. If I put it on the focal points, okay, the image actually is going to be What is it? It's going to be infinity. It's not going to, because that is the point where all the rays from infinity will bounce in. Okay, so the image is going to be at infinity. If I put the object in here somewhere, the image will appear to be coming from the opposite side, and it's actually magnified. Okay, so depending on where I put it, if I put the object of course, I have to put the object always on this side of the mirror. I mean, if I can't put it on the side that is coded, okay? I mean, it doesn't make sense. There is no reflection in there. I mean, if you go behind the mirror, you're not going to see a reflection of yourself. That's the point I'm trying to say, on a flat mirror, that is. Same thing in here. You have to put the object on this side. But if you put it far away from the focal point, you're going to produce an image that is real, inverted, and it's on the same side, okay? So it's a real image, inverted, but it's flipped on its side, that's all, okay? Reflected, if you wish. If you put it on the focal point, you're not going to see an image at all. The image will disappear. It's gone. If you put it between the focal point and the mirror, the image will be virtual because it's going to be on the other side of the mirror, and it's going to be straight up. It's not going to be inverted. It's going to be not upside down. It's going to stay in its direction, and also it's going to be magnified. Actually, the magnification will be more than one. So that is basically how concave mirrors work. The focal point in here is positive, and the object is always positive. The image will be positive if it is on this side. The image is going to be negative. So on this side is negative, on this side is positive. And that's part of the quiz that you're going to have at the end when you watch these videos. So again, the focal point is positive. The image, of course, the object is always positive. The image is going to be positive if the object is actually further away from the focal point. If the object is actually at a distance less than the focal point, the image will be negative. And it's going to be virtual. And it's going to be straight up. And it's going to be magnified. If the object is at the distance more than the focal point, obviously the object is positive. The image also is positive. The focal point also is positive. Everything is positive. The image is real because you can put a film in here, it's going to develop. The image is inverted, and usually the magnification is less than 1. So that basically answers all the questions for the concave mirror. For the convex mirror, it's different. So here is the convex mirror. Again, now the coded area is actually on the inside. Again, this is the axis of symmetry. And if you have an object in here, okay, and you throw it in, obviously here is what it looks like. So now here is the normal. So it's going to, ray will be reflected in this direction. So it appears as if it's coming from here. This is the curvature radius, R, and this is the focal point, which is usually R/2 for well-manufactured mirror, okay? Now, the object is going to be here. The image is going to be on this side, okay? And it's always going to be on this side. So the image is, the object is always real. But here's the problem. The focal point is negative. This is the negative side. This is the positive side. Always the side of the object is always positive. End of story. Okay. And the focal point is negative. The image is virtual. It's always virtual for this case. And like the previous case, that can be real or virtual depending on the position of the object. If the object is a distance less than the focal point, the image is actually virtual. But if it's a higher distance than the focal point, then the image is actually real. But the thing with it is, when it's sitting on the focal point, then you have a problem, okay? So in this case, again, you have the object is always going to have a real image. If it's far away, it looks smaller, okay? And it actually looks different, okay? So, okay. And the image is going to be straight up in this case, and is going to be at whatchamacallit. The image is always virtual, because if you put a film in there, nothing is going to develop, because this is on this side. Okay, there is no real object in there. So for making images and how they form, usually you have to follow at least find 2 points. Okay, have to find 2 points. In this case, the way I found this image in here, all I did was find the normal. So how do I find the normal to a surface? It's the tangent to the surface. So if I give you a surface in here, it doesn't matter if I give you this surface and tell you, I want the normal here. So in this case, you find the tangent to the surface, and this is the normal to that. So if there is a ray that comes in here, it's going to bounce in here. That is the law of reflection. Okay. On this point, though, this is what the tangent is, and this is what the normal is. So this is, again, the angle of incidence and the angle of reflection. And this side in here, it's actually, this is the tangent, and this is the normal to it. So again, this is how you do it. So because I'm dealing with flat surfaces that are supposed to have been constructed well, so the surface in this case is here. Here is actually here. And in this point, this is the tangent. So that is how you're going to find it. First of all, find the tangent, find the normal to the tangent, and then apply the rule. Okay, so if this is really the tangent, this is the normal to the tangent, this is the incidence, this is the reflected. But for me, it appears to be coming from the opposite side. Okay, so this is in a nutshell up to the mirrors. Then the lenses are slightly different. Okay, for lenses, which are actually part of the next chapter, but they're actually chapter 18, which we're introducing today too. Lenses are actually use the concept of refraction. So let me again demo for you guys the concept of refraction in here. If you take a cup of water, and you can do this experiment at home. I have a cup of water that is partially filled with water. This is clear water, no magic in it whatsoever. So if I take a pen, which is a pencil, I'm sorry, which is in this case straight up, and if I put it in here, you will notice that there is a discontinuity right on the surface where these two appear. So if you look at it closely, the line is of the pen is coming straight, and then it breaks up. Pen is still normal. Okay, so this is what we call a refraction, or bending of light between two surfaces. So what I have in this example, I have the water and the air, because this cup is half air, half water at this point. So the light that you see with your eye coming off of the pen, the light has pencil, I'm sorry, coming off of the pencil, reflecting to your eye through the camera, should also have that same exhibit, that thing. Because now light that is coming in here is traveling with the speed of light, light coming from the bottom is traveling with the speed of light divided by the index of refraction for the water, which is 1.33. So it appears to be bending, and that is basically what the law of refraction is. So lenses use this principle. By the way, we will be dealing with this law a lot, okay? For the case that I'm dealing with in here, index of refraction for air is 1. So you hardly will see that. So if there is, in the case of the water, the index of refraction is 1.33. So if you're trying to find, if you're curious, trying to find where the angle of incidence is, it's not going to be, I mean, the refraction, it's going to be bent toward the normal if the incident light is coming from a lighter material to a thicker one. Okay. The opposite is true if the source of light is coming from the bottom. Let's take the example in here. So this is the normal. This is index of refraction higher, and this is air. Okay, so this is water, for example, and that is air. If light is coming from here, okay, so this is the angle of incidence, theta incidence, okay? So this is where the light is coming from here. It's going to bend away from the normal. So this is actually the refracted ray, I'm sorry. So this is the angle of incidence, theta I, this is the angle of refraction, theta R. Again, it's all governed by the same law that we're talking about. So in this case, I'm going to call this one medium 1 again, and this is medium 2, except medium 2 has an index of refraction higher than the other one. So what I say in this case is 1.33 times sine of theta incident, which is theta 2, is equal to sine of theta of the other medium, because I'm taking the other medium to be 1. Otherwise, I will have to multiply by its index of refraction. Here is something of interest, and I know it's discussed extensively in the book and in one of the videos. What is the angle of incidence theta 2 such a way that the ray, when it's reflected, it's going to make a 90-degree with the normal? Here is what I'm saying here. Again, these are the two media. This is the normal. So I want an angle where the ray will come in here, and the angle of the ray that is going to bounce back is going to bounce back right on the surface. In other words, if I'm looking in here, I will not see anything in there. If there is a fish in here that is reflecting light from all just its surrounding to be seen, but if it's right at that angle, which I'm going to call a critical angle, then I will not be able to see it. So this is the condition of total reflection. So this angle is 90 degrees. That's what I'm saying in here, that this one is 90 degrees. That's all. And we want to find this angle theta 2 in such a way that this is true, okay, for the case of water. Well, in this case, what we have n for the water, which is 1.33 times the sine of this critical angle, theta c, must be equal to 1 for the index of water and the other side, which is air, times sine of 90 degrees. If you punch 90 degrees in a calculator, this sine is equal to 1. So basically, this whole thing is 1. So what is the theta c that makes this whole thing work? Theta c is the inverse of the sine that makes this ratio true, 1 over 1.33. Okay. So what is the value? You can just punch it on the calculator, but you will find a condition with which this is the angle from which the fish cannot be seen. If the angle is less, let's say, for example, the fish decides to venture in here, there will be a reflection in here. You can see it. If you're standing in here, you can see the fish, except you will be thinking that the fish is somewhere in here, but it's actually here, because in your perception, you will always think that light is coming straight out, because that's how we were conditioned to. When you see something, light is coming straight from it. But the fish is actually closer to the normal than you think. So if you try to grab it, you're grabbing nothing because the fish is on the other side. But if the fish decides to stay in here, less than the critical angle, I mean, greater than the critical angle, because you're measuring it from the normal. If it decides to stay on this direction, so actually the light will be reflected and you will never be able to see it. So if it bounces up a little bit to the surface, you're not going to be able to see it. If it goes down, it's going to be seen. If we do this experiment in class, if we were in class, we usually do this experiment. You take not this cup, not the clear cup. You take a, like, for example, a styrofoam cup or something, and you put a quarter in it, or a nickel or a dime, whatever you want to, and you put a little bit of water in it. There is a position that if you come closer to it, you're going to see the dime or the quarter. Beyond it, you are not going to see it. If you empty it, even if you're standing at that distance, you will not see it. So this is how we normally do it in class. You'll put a coin in there, and you stand right next to it so that you don't see it. So this is not for that experiment, basically. You have to really have a cup that is not transparent. You have to have a cup that is non-opaque cup, like, for example, made out of styrofoam, coffee cups, okay? You put a coin in, and you stand away from it so that the coin you cannot see. But if you bring water and you start to put water while you're not moving, your classmate, for example, put the water in, you will see the penny all of a sudden starts to appear. And that is the reason why it is because actually it's in a position that you bring the critical angle to be seen. So you're using the reflection to your advantage at some points. But if you put it at a distance in such a way, the height of the water is not high enough, so it's still hidden. So in this case, it's in this condition. So even if you put a little bit of water, the water is shallow enough so that you don't see it. But if you put more and more and more water, you're bringing more and more of that surface so that you're going to get that angle of reflection. Okay, refraction. Okay, we still have a few things to discuss. Namely, we discussed the law of refraction now, and we're going to talk about lenses, which makes lenses interesting. So this is basically what I mean by a lens. This lens is actually in your eye. The first piece of your eye is actually a lens, okay? And there are muscles on your eye that tend to make that, to pull that lens either smaller or bigger, okay? If they're relaxed, the lens is as thick as it can get. If you bring an object up close and trying to see it, actually the eye muscles work hard to make the curvature less, change the focal point. That's what they do. If you look at the eye, this is how the eye would look like, okay? Roughly, okay? So there is that protective layer in there that is made out of the clear material. And then you have a lens, and you have a lens in here, okay? That's made out of also of kind of mainly water. So its index of refraction is actually mainly 1.33, okay? This is where you want the image to be formed. You want the image to form right on the sensitive part of the retina, where it's made up of cones to basically collect the light that falls on them. So if you're looking, for example, at an object in here, for example, a candle, you would want the image to form in here, and the image will be actually inverted image. Okay. So the image is going to be, so we know where the image is, at least for a normal eye. For an eye that needs correction, either the image forms far away or the image forms up front, and you would need lenses to correct it, either to push the image back or to bring the image forward, one of the two. So that's basically the only two things you can have, either a concave lens or a convex lens. A lens to help your lens to push it back, or to help it actually bring it so that it falls right on the nerves that collect the light and send it to the brain, so that the brain will explain what's going on with your image that you're looking at. Okay. So we know where the image is. So that is really this distance, which is a few centimeters. I think it's about 2 centimeters, 2.5 centimeters or something for normal eye, because there are some eyes that have they have depth in them, and usually the image form in there, or they have short eyes. So you can have a long eye or short eye, depending on what's going on. And again, you will have corrective lenses, and that's normal. I'm wearing them. A lot of people do, so there is no shame in it. Okay. Anyway, so that is what the image is. So we know where the image is. Now you're looking at an object far away, and there is no problem. So your eye is relaxed, and the muscles there are fine, and your eye is not gonna tire. You bring an object, a tiny object, and you try to see it far away, you don't see it. So you bring it closer and closer to your eye, and then your eye really have to work hard to change the focal point, the focal distance, to bring it up to more focus so that you can see it. There is a distance in here where the eye will be relaxed. After that, it starts to struggle. And that is about 25 centimeters for normal eye again. As you age, this distance increases. Okay, that's why you will see people, especially as they get older, they have to put more and more glasses. As you're young, usually this distance, you can bring an object very close from a young child and they will be able to see it with great detail. Things starts to be fuzzy below this distance, okay? At higher distances, they will look fine. Okay, I think I have introduced enough this topic. We talked about the eye. We're going to talk more on lenses in general as they are used in optical devices. And then we're going to introduce some optical devices. We're going to talk about the cameras, telescopes, microscopes, and how they use a combination of all of these devices to make optical instruments. That is what chapter 18 is. And then we will do some problems. Sounds good, guys?
Yeah.
Okay, very good. So I'm going to see you guys this afternoon at 12:45 in the lab. I know there is a class before us, so when we go in, please, you have to be careful, okay? There is probably a group of students who are not done with their instructor, so let's give them time. I think they end about 10 or 15 minutes before our class, but sometimes they hang around a little later. So that's all I'm asking, that you guys will basically give them a little bit of room before we go in. Thank you, guys. I'll see you later. I'm gonna stop sharing. I'm gonna stop
Professor.
recording. Okay, bye.